Up next, we do have Daniel and Nikos from Expedia talking about automating chaos attacks.
Hello, everyone. I believe we can start if you can hear me well. Okay, so I'm Nikos. I'm a software engineer at Expedia Group. And today with my colleague Daniel, we will be talking about our journey towards automating chaos attacks. First, a few words about Expedia Group, just in case you don't know us. We are a pretty big family of popular brands in the travel industry. And examples here include Brand Expedia, Hotels.com, Verbo, and more. You probably identify a lot of them. And as you can imagine, each and every incident matters for us. Each and every incident, first and foremost, impacts our customers, but it also harms our reputation. And hence our teams have been exploring chaos engineering for quite some time now. So the presentation for today is divided into two main sections. In the first section, we're gonna focus on fault injection in our applications and as part of our CI/CD pipeline. After that, Daniel will focus more on platform attacks, automated attacks, and in particular, random pod terminations on Kubernetes, which is happening in production. Starting with the first part of the section, let's consider the following use case. This is the property reviews on the Hotels.com website. One of the fascinating features our data science teams have been working on is to sort the property reviews based on what we call usefulness or helpfulness. And that behind the scenes uses machine learning. You can see how this would be displayed to our customers, our users, in the image on the left. But of course, we need to have a fallback logic for that in case something goes wrong. And so we have the default sorting options, with one of them being to sort the reviews by date. You can see that in the image on the right. So now, this could be a very simple architecture for what we talked about earlier. We have service A, which is the service that returns or actually shows the reviews on the website. And service A calls service B. You can think of that as our machine learning platform. So service B is going to sort the reviews and return the reviews based on the machine learning logic. But as we said, we have the fallback logic, which is that service C is gonna be called as a fallback and is gonna sort and return the reviews based on the date now. How can we make sure that this architecture is resilient? It is a simple architecture, but how can we make sure that it is resilient and that our fallback is gonna work? Usually in chaos engineering and in chaos experiments, we define first our steady state, but also our hypothesis. And our steady state here could be that when service B is healthy and accessible, the property reviews will be sorted based on the usefulness, based on the machine learning logic. You can see that in the architecture diagram in the image on the left. And you can also see what our users would expect to see in that case. And then regarding the hypothesis that we want to validate or verify here, our hypothesis is that when service B is not healthy for all sorts of reasons, we should be falling back to service C and return and sort the reviews by date, which is our fallback. Again, you can see that in the architecture diagram. We can either cut connection, the service B could be unhealthy, could be completely down, the connection could have issues and so on. And in that case, we should fall back to service C. Now, how can we implement all that? In general, our teams try not to reinvent the wheel. And what this means is that we either make use of libraries like open source tools and libraries, or of software, licensed software that already exists. And in that case, we use these two libraries. The one is called test containers. The other one is called ToxiProxy. They are both open source. However, the tool doesn't really matter. There are so many tools at the moment. You can use whichever you prefer, really. And then what we can do with test containers is that we can create a proxy for service B, as you can see in the snippet on the right. So we create a proxy for service B. And then with toxic proxy, we inject the failure. And the failure in our case is going to be that we want to cut connection to the proxy that we created for service B. After that, we have additional steps where we verify that service C is called. And if we could tie all that to a user interface, what we would expect to see in the UI would be, as we said earlier, the reviews now sorted by date because we are calling our fallback. So like writing these resilience tests is just one part of the solution. Another big part of the solution is to make sure that these tests are running on a continuously basis. And this is in order to make sure that we don't introduce regression bugs. In that case, our teams have two different, let's say, strategies. The one is to have pre-merge checks before we merge any changes to our main branch. And then we also have post-merge checks or stages. In terms of pre-merge checks, we run our main build, our functional tests, maybe more, and also our resilience tests, which is exactly what we talked about earlier. And then once a change set is merged to the main branch, and before deploying that to our test environments, we run again the entire test suite. This could include, again, the functional tests or the resilience tests, and probably more, things like SAST scanning, etc. And obviously, after that stage, this doesn't mean that we deploy to production. There are a lot of safety nets after that. We do multi-region deploys. Most of our teams do canaries. Many of our teams even have automated rollbacks and progressive deliveries. So up to that point, one could argue that these are not really case experiments, right? Because what we are doing here is testing, and this has a Boolean outcome. The tests either passed or they failed. And we could agree with that. However, the way we like to think about it is that whenever someone identifies a hypothesis that has failed as part of a case experiment or as part of an incident, they can write those resilience tests and continuously verify their systems by simulating those conditions. So in the next section, Daniel is going to focus more on platform attacks, which we could say are more of chaos experiments because these are also happening in production for us. And this is fascinating. So I'll leave this to you, Daniel.
Hi, everyone. My name is Daniel, and I'm going to show you how you can move on to the next level. And that is, instead of running tests in a vacuum or in a controlled environment like a build pipeline, as Nikos mentioned, where you just test for or you just validate for known flaws, we're going to try instead to run tests to create new knowledge that tell us something that we didn't know before about our systems. In this next example, we're going to attack an application that is running in Kubernetes, which is the container orchestration system that we use at Expedia. So this is a picture of a service graph of a small subset of systems at Expedia. Actually, of one of the brands that we have, in this case of hotels.com. Our legal team, they made us change the names of all of the services displayed here. But other than that, this was a real experiment that we ran. We're using Haystack, which is a distributed tracing system, and it works with Zipkin to create this visualization. And each of the names that you see here corresponds to a service. And the color represents the health of that service. Blue means it's healthy, and red, there's no red at the moment. Red means that the error rate is very high. So we start our experiment by terminating just one replica of one of our services, in this case of a service called Wilson. And we do this manually. And since we're using Kubernetes, what this means is that we're simply deleting a single pod. And the expectation here, and we were very certain of what was going to happen because we had tested these failure modes before in isolation. So the expectation here is that we would not see any degradation at all because we had configured multiple replicas and auto-scaling for this specific service. Surprisingly, what happened was a bit unexpected. So we saw a cascading effect in the failures. You can see in the picture that there's a whole lot of red everywhere. So the original service Wilson is broken. This other one called Hopper also broken. And then a few others that are not looking great. Now, what caused this is not important. So the point of this slide is to show you that if you poke your system with a stick, you likely learn something that you didn't know before and something that you couldn't predict. And the reason is that the more complex your system is, the more relationships between different components exist, the more components exist, then the more difficult it is to predict the boundaries and the consequences of a given failure. Say, for example, one service is broken, another one is slow at the exact same time, and then you're maybe redeploying a third one. It's very possible that the combination of all of these three completely separate and independent things happening at the same time, it may create the perfect storm. And these are the kind of things that are very hard to replicate and to test in isolation. And that's where the value of running these experiments lie. In this particular example here, and just as a side note, this was caused by a combination of poor health checks and an incorrectly defined auto-scaling policy. After running these manual experiments for some time, and because they were very time-consuming, we took the next step, which was to allow our teams to opt in to automated attacks. We picked Kube-Monkey. This is on GitHub. It's an open source project, and we picked it to achieve this. There are many other similar tools out there that do the same, or probably even more. The way that this particular one works is it's very similar to Kube-Monkey from Netflix, but instead of targeting EC2 instances, instead it picks a random Kubernetes pod and it terminates it. And what we're trying to achieve with this was actually two things. Obviously, we wanted to improve the resiliency of our system by running these attacks, by finding and fixing flaws. But more importantly, and because these are very basic, very simple attacks, we also wanted to create this culture shift where our developers would start to become more familiar with topics of chaos and to start adopting resiliency practices. And also to create a mindset that things can go wrong at any time, and we just need to embrace failure and prepare for it. And that includes many things, like, for example, making sure that you have good observability and that you can detect when a given system becomes unhealthy and how that is impacting your users. The way that Kube-Monkey works is that you simply need to add a couple of annotations to your pods. These annotations, they just say if your application should be targeted or not, and the dimension of the attack. So should it kill just a single instance, or maybe 50% of the fleet? That's really up to you. In Expedia, we use Helm, and we have a base chart or a base configuration template that can be extended by different services. By using a base chart and by not using these annotations explicitly, we have some flexibility. For example, we may want to move from Kube-Monkey in the future, and this layer just makes it easier for us to do that change. We can also restrict what teams can or cannot configure. So you can see in this example here that the only options that they have available is they can either turn it on or off, so they can opt in or not for the attacks. They can control how big the attack is going to be. And we hide all of the other options. We also integrated these attacks with some of our existing monitoring tools. And again, this is foundational. If you don't have good observability, then there's no point in running a chaos attack. You won't be able to detect what went wrong. You probably won't learn anything from it, and you'll likely impact your users. And then the tech leadership in your company, they won't ever let you run a chaos experiment again. In our case, we already had good dashboards, logs, metrics, traces, but we extended that with these notifications. And they just let us know when these attacks are running, just so that it's easier to correlate the possible problem with one of these attacks by Kube-Monkey. I could spend hours listing all of the different problems that we discovered by running these simple termination attacks. Obviously, I'm not going to do that. We don't have time. And chances are that most of these will be unique to Expedia, just because our tech stack is probably very different than yours. But I think that this one is a particularly good example. So during these Kube-Monkey attacks, what typically happens is you terminate a replica, and then Kubernetes will create a new one to replace the one that was killed. In this picture here, the lines are just displaying the duration of requests. And this black line that you can see, it corresponds to the new replica that was created. And we noticed that the vast majority of our services would display this pattern, this behavior. So the very first request would be extremely slow. And it makes sense. I mean, cold start is not something new. It's actually a very common problem. You have thread pools, you have connection pools, etc., that need to be warmed up. If you're interested in, or if you also have this problem, you can check out this open source project at the bottom called Mittens, which you can use to warm up your apps, and which is what we use to mitigate this issue. And now back to Nikos.
Okay, so far in the first part of the deck, we talked about libraries that you can use to write resilience tests, which run as part of your CI/CD pipeline. And after that, Daniel focused on, again, additional tooling that you can use for automated platform attacks, in particular attacks on Kubernetes. And it feels like we are trying to pass the wrong message here. That's why we will close this presentation with this final slide, which explains a common misconception around chaos engineering. We call that the chaos engineering iceberg. And what this says is that at the moment, many or probably most of the teams are focusing too much on the tooling. And there are a ton of tools out there. We could probably say that there are more tools than teams doing chaos engineering right now. However, we believe the focus should not be there. The focus should be more on the experiments and on the different phases before and after the experiment. We need to focus more on the pre-experiment analysis, as part of which we may find that our observability is not great. We possibly have too many dashboards or too many alerts, or our dashboards are hard to interpret. We should focus more on the post-experiment analysis, as part of which we could possibly realize that there is a lot of toil that could be eliminated using automation. And finally, we should really focus on the culture. That is, how do we create a culture around experimentation and around knowledge sharing? Because after all, knowledge extraction and knowledge sharing is probably the biggest part of chaos engineering and of chaos experiments. And with that, we will close the presentation for today. Thank you very much for your time. I guess we have time for questions. Thank you.
Questions, and there are a few questions. So while we've got you, thank you for that fantastic talk. One of the first questions that came in was about scalability. So the question is, did you have scalability issues with introducing resilience checks to the project repositories? And how did you approach the issue? And do you have any tips or advice from how you rolled that out?
I can answer that one. So I suspect when we say scalability issues here, we mean how to scale the whole chaos engineering problem. And so on that, of course, we have scalability issues. Initially, we started with only a few teams doing that, which were more advocates of chaos engineering. We tried to promote that with talks, with chatting with different teams about their problems. But I think at the moment we are in a stage where we are still trying to scale, because we recently started working a lot with all the brands of Expedia, which means that the scalability issues are actually a big challenge for us right now.
I would just like to add one thing. If you're just starting, I think it's really important if you try to connect with like-minded people, so folks who are also interested in doing this. I think that helps a lot. But then you'll get to a point where even if you have support from leadership, etc., in big companies you have a lot of fragmentation. So even if you have the remit to do this, it's still very, very difficult. And that's why one of the things that we tried to do was, for example, those base configurations, to provide something that would make it easier for teams to start running these attacks and to start doing these experiments.
So I'm curious along the lines of that. One of the questions that came in was essentially around that, right? If you're providing the base experiments, who's performing the hypothesis validation?
Yes, that is a good question. So on our side, and let's say for Kube-Monkey, we run those automated attacks. So basically, end-random attacks, which means that a tool like that is gonna create a schedule, and it's gonna run those attacks. And the problem I think we had initially was that teams were not paying too much attention on those attacks. And after all, what we were really wanting, what we were looking for getting, which would be the knowledge extraction, as we said at the end, was not happening. So I guess in my opinion, it is very hard to have a central team doing those attacks, at least in a big company. You need to find a way to promote that to the teams, because the application owners are the people that have the knowledge of their apps, and the ones that should be creating the hypothesis and the steady state and so on.
And sorry, and just to add on that, I was trying to look at the questions, but I don't know where they are. But just to add on that, I think that there's maybe two pillars here. One is it's really important to be able to provide these capabilities, and that's one of the things that we invested a lot in. So you need to be able to somehow run these attacks, and to make it easier for teams to opt in. And the other part, which I think is more to the point that you were making, Jason, is that maybe it helps if teams can do, for example, GameDays, or that's where they would actually be able to use these capabilities and these tools that we are providing, and come up with their hypothesis and come up with their own experiments.
Yeah, I think that's a great point, and it comes back to something you said earlier in the presentation about chaos experiments versus chaos testing. And I think that question points out the need for both, right? The idea that automating is fantastic because there's a lot of reliability that we know our systems and applications need to have, but there's also that exploratory time for experiments and how do you learn. And so both of these things are very complementary.